In this lecture, we will be covering variability for Psychology 210. I'll start with an overview of the topics that we will be discussing during this lecture. First, we'll be going over the shape of a distribution, which you probably already went over a little bit in central tendency and frequency distributions, but we'll go over it one more time. Next, I'll introduce the idea and concept of variability, and then we'll move on to how we calculate variability. The first way that we calculate it is through the range, and then we'll move on to standard deviation. In order to calculate the standard deviation, you'll need to learn about the sum of squares and variance. And finally, we'll go over the empirical rule, which is really important for when we move on to inferential statistics. Now, as you probably remember, when you graph your data, you might get a specific type of shape for your distribution, and this tells us a little bit about the people who are in our sample or population. So instead of drawing an exact frequency distribution, we can just describe the shape of the distribution, where the x-axis is the scores that we might have in our sample or population, and our y-axis is the frequency. So you can see that in this particular distribution, our most common scores are the ones in the middle, near the mean. And as we get more extreme to either low scores or high scores, we get fewer and fewer people who score in that range. Now, the type of distribution that you have can vary. And we like to describe the shape of a distribution not only because it's fun, but again, it tells us something about our sample or our population. Do they tend to score on one side or the other of a scale? Do they tend to cluster around the mean? Are there two answers that seem to be particularly popular? Those types of things are the things we're really talking about when we talk about the shape of our distribution. So for example, we can say whether our distribution is symmetrical or skewed. If a shape is symmetrical, it means the left and right sides are mirror images. So you can imagine folding the graph or the shape in the middle and seeing if they would match when you folded them over. So for example, here we have a symmetrical distribution. As you can see, if we were to fold it along the dotted line, the two sides would match each other. But sometimes we can also get this type of distribution, which clearly has two responses that were popular among our sample or population. But again, if you were to fold it down the middle and cross it over, you would see that they're mirror images of one another and they would match. So again, this begins to tell us a little bit about our sample or population. Do they tend to answer more with one answer, two answers? And if so, how do those answers relate to one another? However, we can also get a distribution that's skewed. And this simply means there are more scores on one end of the distribution or the other. The other side, so the side that has very few scores, is what we call the tail. And this kind of makes sense because it looks like a tail. So when you're describing whether it's positively or negatively skewed, you simply have to see which way the tail points, and that will tell you if it's positive or negative. So here we have a distribution that clearly is skewed. We have more responses here on the left side than we do on the right, and our tail is pointing this way more positively, so towards positive numbers, and that would be a positive skew. However, in this distribution, we see that we have more answers to the right, and our tail points towards the negative side of the distribution, so we have a negative skew. Again, whether a distribution is skewed tells us a little bit about our sample or population. So in a positive skew, we see that for whatever reason, our participants are answering towards the low end of the scale. And this can be important. And on the negative skew, our participants are answering on the right end of the scale. Again, telling us something about the people who we've surveyed or asked. So when we talk about a distribution, the first thing we might notice or talk about is the shape, just the way I went over the last few slides. And then we might also talk about the central tendency. So as you learned from chapter 3, we have various ways to talk about the central tendency of a distribution. We can talk about the mean, we can talk about the median, or we can talk about the mode. And different types of distributions will have one type of central tendency that is the best representation of that distribution. And you learn that in chapter 3. Now we'll talk about the characteristic of variability, which is another way to describe your distribution. And this becomes very important when we move on to inferential statistics. So when we talk about variability, what we're talking about is how spread apart our scores are. So in this particular distribution, we can see that the variability makes the distribution seem very narrow, especially when we compare it to this distribution, which is much wider in its variability. So even though, for example, these two distributions might have the same mean, right? So these both could come from samples that have a mean of, let's say, 10. How scattered the different scores are seems to be very different. Here, they're mostly around that mean. Here, they seem to really go far away from that mean. So that difference is what we talk about when we talk about the variability of a distribution. And in this lecture, we'll quantify it. So we'll be able to capture it through a formula. So what do I mean in terms of a definition of variability? What variability is a quantitative measure of the differences between our scores. So like I said, we will be using a formula to come up with a number that stands for the variability of our distribution. What this number tells us is whether the scores are spread out, like we saw in that more wide distribution from the last slide, or clustered together, which we saw in the narrow distribution from the last slide. And it tells us what the distance is that we should expect between one score and another. So on average, how far away are the scores from one another? Are they only half of a point away from each other or 10 points away from each other? This again will become very important when we learn inferential statistics, but it also tells us a lot about the sample or population that we're working with. Importantly, the variability also tells us how well a sample likely represents a population. And as you learn from Introduction to Statistics, we really want our sample to come as close as possible to our population in terms of the variability in the types of people who might be in that population. And so now that we can quantify the variability, we can actually see if it comes close to what our true population is. So again, it's going to tell us, are the scores clustered together or are they more spread out? One measure of variability is what we call the range, and this probably seems intuitive. It's simply the distance covered by the scores in a distribution. So for example, if I take a sample of people and ask them their height, we'll clearly have one score that's the lowest within that sample and one score that's the highest within that sample. And the distance between that lowest score and that highest score is what we call the range. So from the lowest to the highest score. The way that you would calculate the range is by subtracting your smallest score, so x min, from your largest score, so x max. So if, for example, you had someone who was 4 feet tall and someone who was 7 feet tall, your range is 3 feet, right? So you would take 7 feet minus 4 feet, and your range is 3 feet. However, this is a somewhat crude measure of variability. It doesn't tell us a whole lot other than really just the distance between the highest and the lowest scores. It doesn't really tell us a lot about what's going on in the middle. And we really want to know a little bit about all the scores, not just the highest and lowest scores. As you learned with frequency distributions, sometimes we can have an outlier, we can have an extreme score. So if our person who's 7 feet tall is the only person anywhere near that height, let's say everyone else is 6 feet or below, that range is not really giving us an accurate description of the variability of our sample. A range is good though when we're checking the operational definition of a new variable. So if you remember, an operational definition is simply a behavioral characteristic that we can use in place of a construct. So for example, shyness. We might take not talking to people at a party as a definition of shyness, but we want to make sure that people vary quite a bit on the way that we define this variable. And so the range is good to make sure that people are behaving in a way where you can really capture differences. In addition, if you make up a new scale, let's say you have a scale from 1 to 7 on happiness, you want to make sure that people are ranging from 1 to 7 and using the entire scale and not simply clustering at the top or the bottom. So the range is good to check the operational definition of a new variable. But when it comes to knowing something about your sample or population, it's not the best measure of variability. What is very useful for us is what we call the standard deviation. So let's talk more about what this is. The standard deviation is how a score, of course represented by x, compares to other scores in the population or the sample. So we simply want to see how far away the scores are from one another. And the standard deviation is always based on the mean. Now, if you're talking about the population, this means that you will represent it with the letter mu. If you're talking about the sample, we'll represent the mean with the large letter M. Now you'll need to keep your statistical notation in check here because we're going to start using it a lot. So let's take the example of a quiz that you took in a class. Perhaps you earned a 45 out of 50 and this gave you a 90% on the quiz. And you know that the class mean was a 40 out of 50, which is an 80%. Now, this seems that no matter what happened with the rest of the class, a 90% seems pretty good. And it probably is. But one thing that the standard deviation can tell us is how good that 90% is, even compared to that mean. So it's really about how everyone else in the class scored and where that score sits in relation. So if, for example, the variability of the class is very low, which means that people tended to cluster around the mean. So most scores are somewhere between a 70 and a 90. It means that very few students got above a 90% on this particular quiz. However, if the variability were higher, in the sense that the scores were more spread out, around the mean, this means that a lot more students than in the previous graph got above a 90% on that particular quiz. So as you can see, the variability tells us where one score, in this case 90%, is in relation to the other scores. So you remember that the scores are represented within this distribution, right? So we might have a score here and a score here, a score here and a score here. So your score of 90% is here, and we're trying to figure out how many people do we think got more than that 90% or less than that 90%? And the standard deviation will help us figure that out. So now we will move on to calculating the standard deviation for a population. So remember again that your standard deviation can be thought of as the average or standard distance of any score represented by x from the mean. Deviation simply means movement away from. So we're simply looking for the average movement away from the mean for any score in comparison to all of the other scores. So let's start by figuring it out for a population. The first thing you're going to do is find the deviation of each score represented by x from the mean. Because this is the population, we're representing it with mu. So the way that you put that in statistical notation is to say x minus mu. So we'll take each score and subtract the mean from that score to get our deviation. So for each score, you'll subtract the same number because it's the mean for that population. Now, as you'll notice as you do this, that scores above the mean will be positive because they're larger than the mean, and scores below the mean will end up being negative. And that makes sense since some scores are above, greater than, and some scores are less than our mean. However, if we wanted to find the average the way we normally find the average, which is adding them up and dividing by the number in our population, this would give us a bit of a problem because the mean of the deviations would end up being 0. And that's not a good thing. No matter what your population is, if you simply add up all of the deviations and divide by your number of people, or the number in your population, your mean will always be 0. So we have to figure out a way to manipulate our data so that we can still find a deviation. We're just going to do it in a little bit of a roundabout way. So the first thing you do then is you square your deviations and you sum them. So for each deviation, you're now going to square it, and after you've squared all of those deviations, you then add them all up. So the reason that we square our deviations is to get rid of that problem of having those negative deviations. Because when you square a negative number, the result is positive. So that means that all of our deviations can now be positive. This step, this squaring of your deviations and then summing, is conveniently called your sum of squares, which we will be noting with SS. The next step in the process is to now divide by the number of scores. In this case, it's represented by capital N because we're working with a population. So now that you've squared your deviations, added them all together, and divided by your N, this step is what we call our population variance. And we're going to note that with a little sigma squared. So just like the American alphabet or Arabic alphabet, the Greek alphabet also has capital and small letters. And so this is just the small sigma. It looks like an O with a little cowlick. And so the sigma squared, very important that you keep that squared in there, is our population variance. Now, we're still dealing with these squared numbers, which is why we have the square here in our population variance. So the final step to get to our standard deviation is to find the square root of the variance. And you'll notice that if we simply take the square root of this statistical notation here, what we end up with is simply the little sigma, right? Or the O with the cowlick. So that is how we find our standard deviation for our population. So let's go through it one more time using only statistical notation. So to find your sum of squares, which is represented by SS, you're going to first find your deviations, square them, and then sum all of those numbers. So it's exactly what we went over on the last slide, only now I'm only giving it to you with a statistical notation. Our variance is basically our mean squared deviation. So it's our sum of squares divided by that capital N. And finally, our standard deviation is the square root of this here. So SS divided by N, you take your square root, and that's your standard deviation. So don't forget that we're going to symbolize this with our little sigma, O with the cowlick, and our variance is simply sigma squared. So when you go to find the variance and standard deviation of a population, you should be working with these formulas as you go along. Now, the way that we find the variability for a sample is very similar to the way that we find the population for find the variability for a population. However, there's one difference that is pretty crucial, and this is what you'll have to remember when you're finding the standard deviation, whether you're taking the standard deviation of a sample or a population, because one very important calculation will change. So very similar to the last first step, we first find the deviation of each score, represented by X, from the mean, in this case represented by M, because we're now dealing with a sample. So you first find X minus M, very similar to how we found the deviations for our population scores. So much like the last time, we're going to square those deviations to get rid of those negative numbers and sum them. And this is again your sum of squares, represented by SS. Now you're going to divide by the number of scores minus 1. So in this case, it's not simply n, it's n minus 1. And this is now our sample variance. So some of you may be wondering, why n minus 1? Well, statisticians, of which I am not one, have realized that if you divide by n minus 1 instead of simply n, this actually gets us much closer to the population variance than if we simply do it by n. And many calculations have sort of proven this, that when you divide by n minus 1, it takes care of some of our sampling error. And as you know, the sampling error is simply the difference between our sample and our population that we're going to get naturally. But if we divide by n minus 1 instead of simply n, we reduce a little bit of that sampling error. So our variance and standard deviation can be a little bit more true to what our population variance and standard deviation is. So that's why we divide by n minus 1. And just like last time, we find the square root of our sample variance, and that will give us our standard deviation for our sample. Now we'll go over this again using statistical notation. So our sum of squares looks very similar to our sum of squares for the population. We're simply taking x minus m to find the deviation for each score, squaring it so that we can get rid of those pesky negative numbers, and then summing all of those squares. And that's our sum of squares, still noted by SS. Now, our variance, or our mean squared deviation, is found using SS divided by n minus 1, again, to get rid of a little bit of our sampling error. And to find our standard deviation, we simply take the square root of our variance. So we take SS divided by n minus 1 and take the square root. So now we're going to note the standard deviation for a sample with a lowercase s and the variance of our sample with a lowercase s squared. So much like our population where we had sigma here and sigma squared, for our sample, for our sample we're using s and s squared. So one thing that I really want you to pay attention to is the difference in the statistical notation of whether we're dealing with a population or a sample. And the reason for this is that you don't necessarily have to memorize all of the formulas as long as you know which one to find when you need it. So once you figure out if you're dealing with a population or a sample, you'll know which formula to go to when you're trying to find your standard deviation. And that will be because of the statistical notation used within the formulas. So keep in mind that for step 1, when we're finding deviations, for the population, we're going to see x minus mu. Scores are still always represented with x, but our mean is going to be represented with mu for our population, but with m for our sample. So if you're looking up your standard deviation formula for a sample and you see x minus m in there, you know that you're on the right track. The next step is finding the sum of squares. Again, these formulas look very similar. The only difference is how we represent our mean. In the population, we have the mu. In the sample, we have the m. Now, the variance is where we start to differ, right? So for our population, we're simply dividing by our large N, but in our sample, we're dividing by n minus 1. So this difference here is where a lot of students get confused. And unfortunately, if you're finding the standard deviation for a sample and use your entire n, that calculation is not correct. Again, we're trying to take into account our sampling variance and correct for it as much as possible. And finally, when you're figuring out your standard deviation, here we have our square root of our variance, and here we have the square root of our variance. That should be n minus 1. I apologize for that, but it should be this exact same thing here. So the square root of SS divided by n minus 1. So what I want you to do is simply get comfortable with the notation, right? Because that way you don't have to memorize the formulas, but you can go ahead and look to the formula that you need and know from the statistical notation whether you're using the formulas for a population or a sample, and if that is what you should be using given the data that you have. So let's finish up the lecture by talking about the empirical rule. Now this rule is going to become very important when we talk about inferential statistics, but for now I just want to tell you how the empirical rule can help you learn about your sample or population, so the people who you're studying. If you have a normal distribution, so something where the scores tend to cluster around the mean and taper off towards the left and the right, we can start to create proportions, and these are pretty predictable because of the empirical rule. So what we do know is that in a normal distribution, the majority, or 68% of your scores, are going to fall between one standard deviation below the mean and one standard deviation above the mean. So, for example, if we have this distribution here of a population, we could figure out the mean. And using the formulas that I just gave you, we can also figure out the standard deviation. So that means we can figure out one standard deviation above that mean and one standard deviation below that mean. So no matter what that standard deviation is, if it's 0.1, 10, 100, a million, if your distribution is normal, 68% of your participants will fall between that -1 standard deviation and that positive standard deviation. And I think that's pretty cool. Even more amazing is that 95% of your scores are going to fall between 2 standard deviations below your mean. So we have the same mean, but now we're out 2 standard deviations out here and 2 standard deviations out here. 95% of your participants will fall somewhere between those two numbers. Again, it doesn't matter what your standard deviation is. If it's 5, 500, 5 million, it doesn't matter. You can tell I'm getting very excited by this because no matter what, 95% of your participants will fall within those two numbers. Now, of course, those two numbers will be different depending on what your standard deviation is. So if your standard deviation is 5, then this number out here will be 10, and this number out here will be -10, assuming that our mean is 0. But what I really want you to take away from these predictable proportions, is that we can use them to figure out what an extreme score is. So we can start to figure out how a score falls on the distribution in terms of standard deviations. So if it's somewhere between 0 and 1 standard deviation away, we know it's pretty normal. Even if it's within 2 standard deviations, that's pretty normal. But once you start to get out here, only 2.5% of your participants are going to fall into that extreme. So if someone is above 2 standard deviations away from the mean, we can start to see that they're an extreme score. So that's another way that standard deviations help us, and in combination with the empirical rule. And what's great about the empirical rule, as I just mentioned, is that it doesn't matter what your standard deviation is. So you can imagine that the standard deviation for this very narrow distribution is going to be small, whereas the standard deviation for this much wider distribution is going to be bigger. But again, it doesn't matter what that number is. Between 1 standard deviation below and 1 standard deviation above, we have 68% of the population on both graphs. So here, that range might be smaller, and here, that range might be bigger. And we're going to use that a lot in inferential statistics. So it's good to remember that the empirical rule exists, and it really is based on standard deviations, which are going to become our friends. So that's it for the lecture portion on variability. You can move on to the practice problems on the next video. Thanks for watching, everybody. Good luck with your Mu's and Sigmas, and hopefully you can take a break along with them.